Hello, and welcome to video lecture for topic 3, IUPAC Naming. Now I want to start this off by just reminding everybody in the class that my primary concern is that you are able to take a systematic IUPAC name and convert that into a line structure or a structural formula. There are certain compounds where I will expect you to convert from a structure, whether it's a line structure or a structural formula, into an IUPAC name, but those are going to be relatively simple and straightforward. This video is going to cover both directions, name to structure and structure to name, but primarily we're going to be interested in being able to go from a name to a structure more so than everything else. In addition, I want to remind you to take a look at the supplement for topics 2 and 3 that's posted on the Moodle page. At the end of that, there's a list of about 14 different compounds that have what we call common names that are accepted in the IUPAC nomenclature, and those you will be expected to know as well. So be sure that you take a look at the supplement for topics 2 and 3. Okay, so in addition to structural formulas, chemists also find that we need to be able to communicate structural information about a molecule using the written word. And so in order to have a universal and consistent method for doing this, for naming this myriad of organic structures that are, possible, the IUPAC, which stands for International Union of Pure and Applied Chemistry, back in 1949, formulated and codified the rules for naming organic molecules. And we can break this down into 4 parts. So really almost any organic molecule, right, its name, its written word name following the IUPAC system will have 4 parts. At the very beginning are substituents, right? This is field number 1. After that comes what we call the compound root. This is field number 2. After the compound root comes what we call the multiple bond index. That's field 3. And finally, the principal functional group. And this is field number 4. So anytime you see a systematic name, an IUPAC systematic name for an organic molecule, you can break that name down into 4 zones or 4 parts. Substituents at the beginning, compound root following that, multiple bond index third, and finally the principal functional group. So in order to take a structure and, from a line structure or a structural formula and convert that into a systematic name, right, we need to start with what is the compound root. And the compound root is either going to be the longest continuous carbon chain or the largest all-carbon ring. There are going to be some exceptions to that we see later on, but for our purposes, the largest ring or the longest continuous chain is going to be what's going to form the compound root of our compound. Now, I want to take a quick moment and talk about ring structures. There are 2 types of rings that we get concerned with in organic chemistry. One of those is a ring that has only single bonds and double bonds with no kind of pattern to them. So I could have a double bond there, 2 single bonds in between it, a couple more single bonds and a double bond there, right? This would just be considered, what we call an alicyclic ring system. On the other hand, there are a special family of cyclic compounds where we have alternating single and double bonds as we go through the ring, right? If we see this pattern of alternating double bond, single bond, double bond, single bond, double bond, single bond, these are known as arenes. The most common arene and one that you should be familiar with is the benzene ring. And these are two different families of compounds, and they're going to be named slightly differently. All right? So let's move into naming of what we call aliphatic compounds. And so these just straight chain, right? We don't have any rings involved in it. This is known as an aliphatic compound. And so we're going to start with naming there. And so the first thing we need to do is just see how many carbon atoms form that longest continuous chain. So I'm going to throw some carbon substituents onto it. Right? So now we've got lots of carbon substituents, and we've got different chain pathways that we can go through. So we need to find the longest continuous chain. And so really you have to just pick a starting point, right? Having drawn this myself, I'm going to start over here. We see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 if I go down that pathway. If I go up this pathway, that only makes 4. If I go here, that's 4, 5, 6. If I go here, that's 5, 6, 7, 8, 9. Eight and 9, and coming up from this branch point, it's also going to be less than 9. Okay, so now we have two different continuous bond chains. Either one of those has 9 carbons, and so if you look back to that table that's in Sorrel, right, the compound root for this is going to be for a 9 carbon chain, and that's going to be a nonane derivative, so we're just going to put nona here, which indicates 9 carbons in the longest continuous chain. Right? If this were a cyclic system with 9 carbons, we would add cyclo in front of it. We're going to look at some cyclic examples in a little bit, but for right now, let's just finish off this compound. Right? The next thing we need to do is determine which of these two pathways we're going to choose for picking our substituents. And so if I choose the pathway that ends here, I'm going to have 1, 2, 3, and then a weird extra substituent there. Whereas if I choose the pathway that ends here at this asterisk I've drawn, I'm going to have 1, 2, 3, 4 substituents that are easily named. Okay? And so I'm going to choose my numbering system to start from where the closest substituent is. So I'm going to start over here where I have the 1, and I have an ethyl substituent. I have an isopropyl substituent. I have another ethyl substituent. And then here I have a 1, 2, 3, 4 carbon. So this is a butyl substituent. I've cautiously chosen this to make the numbering schematic easier. We are going to go ahead and list these out. So at position 2 and position 6, we have ethyl substituents. At position 4, we have an isopropyl. And at position 5, we have a butyl. Regardless of what the numbering is, when we come to do substituents, we need to do them in alphabetical order based on that parent root for the substituent. So we have one that starts with an E. Here we have one that starts with a P, one that starts with an E, and one that starts with a B. So we have a 2-ethyl, 4-isopropyl, 5-butyl, 6-ethyl. Now notice we have 2 ethyl groups, so we're not going to write them twice in the name. We're going to combine those together to be diethyl. So what does this look like now? If we start with our butyl group, it's at position 5. For our substituents, we're going to start our naming with 5-butyl. Next up alphabetically would be our ethyl groups. So we have at position 2 and position 6, since there are two ethyl substituents, diethyl. And then finally at position 4, we have our isopropyl group, 4 isopropyl. Nana, we have no multiple bonds, we have no functional groups, so we don't need anything there, and this becomes non-ane. So the full name would be (5-butyl 2,6-diethyl 4 isopropyl nonane. And now notice there are no spaces here. Our numbers are separated by commas. Every time we switch from a number to a word, we use a hyphen. 5-butyl 2, hyphen 2, 6, hyphen diethyl, hyphen 4, hyphen isopropyl nonane. This would be the IUPAC systematic name for this compound. Okay, so I went through an example just to show you kind of how this works, and now I'd like to get into a little bit more of the details. So the first thing, right, is just knowing how do we derive these compound root names. So for aliphatic compounds, a 1-carbon chain is going to have the compound root meth. 2-carbon chain, eth. 3-carbon chain, prop. 4-carbon chain, bute. 5-carbon chain, we're going to be at pent. The 6-carbon chain is hex. 7-carbon chain is hept, not sept, hept. 8-carbon chain, oct. 9-carbon chain, non. And then finally the 10-carbon chain, dec. For cyclic systems, so these are going to be our alicyclic compounds. Alicyclic. There we go. All we do is just add cyclo in front of this. So again, these are ring systems that are not arenes. Any ring system that's not an arene is an alicyclic compound. And the smallest possible one, of course, has to have 3 carbons in it. So for a 3-carbon alicyclic, that's going to be cycloprop. 4-carbon cyclobute. 5-carbon cyclohex. 6-carbon, 5-carbon should be cyclopent, excuse me. 6-carbon is cyclohex. And so on. Exact same naming that we have for the aliphatics. Just now, since it's a ring system, we put cyclo at the front. And by far, cyclohexane, cyclopentane, cyclobutane, and cyclopropane will be the most common ones we see this semester. As long as you know this list, just throw cyclo in front of it. So for benzene and its derivatives, there are certain things that I do want you to know. These are common names that have been adopted by IUPAC, as I mentioned earlier. You can also find these at the end of the supplement for topics 2 and 3. So, benzene and derivatives. These fall under arenes. And we have the unsubstituted derivative, of course, is benzene. If we put a methyl group off of that, the IUPAC name for this, toluene. If we put a amine group off of it, the IUPAC name is aniline. If we have a OH group, this is known as phenol. And finally, if we have a oxygen with a methyl group coming off of it, this is known as anisole. I expect you to know these 5. I expect you to know their common name, which is adopted into IUPAC. And you can definitely expect to see one of these, or maybe more, on exam 1 coming to a lecture period near you. So these are our systems, right, for determining our compound root. Right, so I'm going to box compound root here in the same color. And we know that everything that we have around here relates back to determining our compound root. The next thing that we want to look at is how do we determine the multiple bond index, right? So the multiple bond index comes immediately after the compound root in the name, and it specifies the quantity and type of carbon-carbon multiple bonds in the molecule. So this multiple bond index is only for carbon-carbon multiple bonds. It's not for a carbon-oxygen double bond, or a carbon-nitrogen or double bond, or a carbon-nitrogen triple bond. Only carbon-carbon double bonds and carbon-carbon triple bonds. So the multiple bond index is strictly for those 2 scenarios, right? So as we said, if the compound only contains carbon-carbon single bonds, so only carbon-carbon single bonds, right? The multiple bond index and the suffix ane, so our multiple bond index is going to be ANE, which comes from alkane, right? And that is what we'd put in position 3, and that comes right after the compound root. Now, carbon-carbon double bonds have a multiple bond index of ene, E-N-E. This comes from alkene. And carbon-carbon triple bonds have a multiple bond index of yne, Y-N-E, and this comes from alkyne, Y-N-E. List our carbon-carbon double bonds in our multiple bond index first, and our carbon-carbon triple bonds come second. So for example, if I have this molecule here, I have 1 double bond, 2 double bonds, and then a triple bond. The triple bond would take functional group priority. This would be carbon 1, 2, 3, 4, 5, 6, 7, 8. My compound root would come from my 8 carbon chain, so this would be oct. My double bonds would go first, so I have a double bond starting at position 4, another double bond starting at position 6, so this would be 4, 6, diene, and then since it's at the triple bond starts at position 1, we don't need to number it, yne. Okay, again, this di signifies that I have This di signifies that I have 2 carbon-carbon double bonds. And then the ine, because there's only one of it, and it starts at position 1, I don't need to give it a number, but I do have to indicate that it's there, and there's just one of them. Okay, let's go ahead and go through a couple more examples where we look at working with this multiple bond index. Okay, so compound root and multiple bond index for this molecule here. So the first thing we notice is that we have 1, 2, 3, 4, 5 carbons in this molecule, and so we know that our compound root is going to be pent. The next thing we need to do is determine our numbering to decide what position this double bond is at. Numbering from this end gives me 1, 2, 3, 4, 5. Our double bond would start at 3 in this direction. Numbering from this side, 1, 2, 3, 4, 5. We always want to go with the lowest number. Since there are no substituents, nothing else to worry about, we want to start with the lowest number right there. That would be 2. So this would be pent 2-ene. Taking a look at another example, again, we're just going to stick with 5 carbon chains for right now. We now have 2 double bonds here, so our root, though, 5 carbons, our root is still pent. Numbering from this side, 1, 2, 3, 4, 5. Numbering from this side, 1, 2, 3, 4, 5. And I want to pick now, since I have 2 double bonds, I have to do 2 numbers. I want to pick what's going to end up being the lowest sum of the two positions. So 1 and 3, numbering from this side, add up to 4, whereas 2 and 4, numbering from this side, add up to 6. So we're going to go with the 1 and 3. So this would be pent 1, 3. Now since I have 2 double bonds, di, and since they're both carbon-carbon double bonds, di-ene. Let's take a look at an alicyclic example. Here now again I have 5 carbons in my ring, and so that means my root is going to be cyclopent. And now when the ring system comes into play, we have to pick where we're going to start numbering again. And so because we can pick any carbon to begin at, we're going to want to pick the carbons that will result, again, similar to here, in the lowest numbers for any of our multiple bonds. So I'm obviously going to start 1 at one of my multiple bonds. Moving around now, I can either go down to 2 or up to 2. So if I go up to 2, that puts me at 2, 3, 4, 5. Had I gone down to 2, 2, 3, 4, 5. So either direction, my double bonds start at carbon 1 and carbon 3. This is a unique example where we can get away with it, and it's simplified for us. So don't expect that to be the case always. It happens to work here, but you will encounter it. So this is cyclopent 1, 3, diene. We've looked at lots of double bond scenarios. Let's take a break and then look at some triple bond scenarios. So triple bonds work similar to double bonds. We'll just take a molecule here. All right, now if we take a look at this, we see we have 1, 2, 3, 4, 5, 6 carbons. Our compound root will be hex for 6 carbons. Now, again, I've drawn a symmetrical molecule here, so regardless of which side we start at, we're going to end up with the same numbering scheme. We have 1, 2, 3. If I came from this side, it would also be 1, 2, 3. So this would be hex 3 ine for to indicate the triple bond. Taking a look at an alicyclic example. Here now we have 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. Again, I've started my numbering from one of my multiple bonds to keep it simple for me. I see that my multiple bonds start at 1 and 5 if I number in this direction. If I number in the opposite direction, 2, 3, 4. You would think that this is the right way to go, but really, we have to stick with the outside system. We have to include both carbon atoms of that triple bond that we chose our number 1 position to be at. So that rules out that numbering scheme. And this, our compound root is now cyclo-oct. We have 2 triple bonds starting at carbon 1 and carbon 5. Di because there are 2 of them, and ine because they're triple bonds. So our compound name here, cyclo-oct 1,5-diine. Excuse me, cyclo-octa 1,5-diine. Okay, so that takes care of our multiple bond index. So now we need to move on to box 4, the principal functional group. All right, so we've dealt with how do we determine the compound root, how do we determine the multiple bond index, how do we apply those when going from a structure to a name. Next, let's take a look at the principal functional group. Now, organic molecules will typically contain more than one functional group in them. However, only one of those functional groups will be classified as the principal functional group. And in the development of IUPAC naming, the different functional groups were assigned priorities. How and why they were ranked in the way they were ranked was outside the scope of this class. But what we need to do is focus on the priority ranking, right? And so Table 1.1, which is on the inside front cover of your Sorrel textbook. I also photocopied that and provided that sheet to you earlier this semester. Covers the functional group ranking. The functional group with the highest priority, the functional group in the molecule with the highest priority according to that table, is going to be the principal functional group, right? And it is going to determine the last part of the name. So far, we've only looked, in the examples I've shown you, we've only looked at molecules that just have carbon atoms in there. We haven't looked at anything with heteroatoms in there. The most complex functional group, what we've seen, is a carbon-carbon or carbon-carbon double or carbon-carbon triple bond, right? And that applies to our multiple bond index. However, once we start introducing functional groups with heteroatoms in them, our principal functional group is going to change. For alicyclic and aromatic compounds, so alicyclics and arenes, right, this is going to determine the numbering around the ring. And so there's a slightly different set of rules that go there. And you can take a look at Sorrel. He does a really good job of explaining when a functional group is a substituent and it's the principal functional group off of a ring, how numbering works. When it's part of a ring, how numbering works there. I think he does a great job, and I'm not going to really get into that. Your reading should cover it just fine. So our principal functional group always determines the suffix or end of the compound name. It's always the highest priority functional group of all functional groups in the molecule. And those suffixes are listed for you and their ranking and their structures, again, in Table 1.1 inside front cover of your textbook. So now that we've gone through all of those, the last thing there is to talk about are substituents. So the substituents are anything that we haven't covered so far. It's not part of the longest continuous carbon chain. It's not an alicyclic or aromatic system, which would determine our compound root. This is not going to, while they may contain double bonds, those double bonds are not part of the longest continuous carbon chain or largest ring structure in the compound. And the substituents are something different than the principal functional group, which determines the suffix of the compound. Right? And so we need to determine not only what types of substituents are left on our molecule, but also what their numbering positions will be. So let's take a look at a quick example, and this is going to wrap it up for this video lecture. If we take a look at this compound here, which is about the level of complexity that I'll expect you to be able to convert from a structure to a name on our exams. This is about as complex as it's going to get. We're just going to go through these one at a time. The numbers above the lines indicate the position in the name. I'm going to write underneath the order in which we do this. So step 1, determine the compound root. Step 2, determine the multiple bond index. Step 3, determine the principal functional group. And finally, step 4, determine the substituents and numbering. So, here we see our longest continuous carbon chain. We can start here, 1, 2, 3, 4, 5, 6. So our longest continuous carbon chain is 6 carbons. Our compound root will be hex. If we look for now, step 2 for our multiple bond index, we see that we have a carbon-carbon double bond. And we have one of them. We're not quite sure what our numbering is going to be. We're going to determine that based on our substituents. But if we take a look at that, we know that we have one carbon-carbon double bond. So our multiple bond index is ene, since there's only one of them. Our highest ranked functional group, our principal functional group, is going to be the ketone here. And so the suffix for ketones is going to be -one. Again, you can find those suffixes in table 1.1 in your textbook or in the handout that I've provided. And so finally, all that's left for us to do is to determine numbering of the substituents. So I'm going to go over the parent compound chain in a slightly different color so that we can differentiate it from the substituents that we need to find. So there's our, actually I'll just circle it. So there's our parent chain, right? We've taken care of our multiple bond index. We've taken care of our principal functional group. So this is our principal functional group here, this ketone. And so finally, we just need to worry about numbering our substituents. So we have two directions that we can number this compound. We can start from the double bond side, at which point we have 1, 2, 3, 4, 5, 6. That means we would have numbering in our compound at positions 3, 4, and 5. If we started from the opposite end, excuse me, if we started from the opposite end, we could number 1, 2, 3, 4, 5, and 6. In this situation, we would have numbering we would have substituent numbering in our name at position 2, position 3, position 4, and also position 5 to indicate the double bond. Numbering with the blue system, we don't have to include the number for the double bond since it's at position 1. So a good rule of thumb or a good principle to follow is to just add up these numbers and see which system gives you a higher value. We don't want that system. We want the lower value. 2 plus 3 is 5. That's 10. This gives me a total of 14. Whereas numbering in blue, 5 plus 4 plus 3, that gives me 12. The blue numbering fits my needs better. And so now I have a methyl substituent at 3, another methyl substituent at 5. So now to finish off my name of my compound, this would be 5,5-dimethyl hexene 3, hexene. Wow, I just really messed that one up. See, folks, no matter how long you've been doing this, you still make mistakes. Excuse me, that was not 5,5-dimethyl. It should be 3,5-dimethyl hexene 4-one. So again, methyl group at position 3, methyl group at position 5, carbonyl ketone at position 4, 3,5-dimethyl, that's our substituents, hex, that's our compound root, ene, our multiple bond index, 4-one, our principal group and its position. This is about as tough as it's going to look on the exams. I do encourage you to get a lot of practice problems on converting name to structure and structure to name. It is one of the more challenging topics, even though we don't typically tend to devote a lot of time to it in class. It will show up on exam 1 and it will show up again on the final, keeping in mind that that's about as tough going from compound structure to name. When it comes to going from a name to a structure, being able to parse this out and produce a line structure, I encourage you to expect that I will give you much longer names than the one demonstrated here. Thanks a lot, and as always, if you have any questions regarding this, make sure to bring them up in lecture, conference, or stop by for office hours.